Hello, thank you to LED Professional for giving me the opportunity to talk about one of our recent application studies we did. My name is Rob Engelen. I lead the LED applications engineering for illumination purposes. And what we have investigated is how you can make a multicolor LED cluster as depicted here on the bottom right. What kind of LED would be ideally suited to make such an array? So let's dive a little bit deeper into what kind of fixtures you can make with that and where it's used. Well, we have all seen multicolor fixtures being used, for example, in architectural floodlighting to illuminate bridges, buildings, and whatnot. Also in stage lighting, we've all seen theater or entertainment shows with very colorful shows putting up. And also it's used in studio and film lighting. This area has very high requirements on the quality of light, and therefore they also use multicolor LED fixtures. Now, what does such a fixture look like? I depicted 3 different variants here, potentially related to all these 3 segments that I just mentioned. On the left, it's pretty obvious to see this is a multicolor LED fixture where each lens has its own color LED below it, and you can see this rainbow effect on the outside of the fixture. With the right LED, these kind of fixtures are easy to produce, but it has some drawbacks. For example, this rainbow effect you see on the external here, those could show up as colored shadows, and obviously the multicolor appearance might not be ideal. If that is a problem, you could go to an architecture as depicted here in the middle, where the multicolor LEDs are below a single lens. So this can be a cluster of, let's say, 4, 5, or 6 LEDs together under one lens, and then the lens mixes the light so the appearance is uniform. Also, the beam coming out of this, even if you use multiple colored LEDs, it can still make a uniform white. Here, the difficulty is in the optics. The optics needs to mix the light so it's uniform white, and ideally also that the exit phase of this lens is also uniformly colored. This is a very difficult design to make, and the beam quality can never be perfect. If you have really high-end fixtures for demanding customers like in the studio lighting space, then you could look at the fixture here on the right. This is a lamp for studio lighting with very high beam quality and very high color uniformity over that beam and also the exit phase. Think of these lamps as quite big and heavy. These can be 20 kilos each. Also, you can modify the color and also the beam. And the biggest challenge in these lamps is the thermals. And why that is, I'll come to in the next slides. Now, what is below each of these fixtures? On the left, we have our multicolor under one single lens. So here you see it depicted schematically, a single LED under a single lens. And if the LED properties are correct, for example, the exit phase of the light is at the same level, and also the size of the LED chip used is the same, then you could use the same lens in front of every color to still get uniform beams. So for this application, somewhat 10 years ago, we have developed the Luxion C, which you can use very well in such a fixture. To give you an impression of dimensions, the LEDs are 2 millimeters across, and the lens could, for example, be 10 millimeters or 50. Then in the middle, a different configuration with a cluster of LEDs, and these can be 4, 3, 6, 7, LEDs together under a single lens. Now the lens mixes the light, but that's always easiest if this cluster is small. So we have developed for this application the Luxion Rubix, which is a very small LED of 1.4 millimeters across. And with that, you can build arrays, let's say 5 millimeters in diameter of the array. Then on top of that goes a lens of 30 to 50 millimeters to mix the light. Then the last application is a large array of LEDs. Think of 100 LEDs together or more in 20 to 30 millimeters diameter. Around this LED array is then, I sketch schematically here a reflector, but it can also be a more complex optic like above, where you can still do some zoom, change the beam diameter and such. But in essence is this. So why is this a big thermal headache? Is because all the energy is concentrated to this 20 or 30 millimeters array. And you need to dissipate that heat in order to keep the array cool or at least not overheating. So this is the topic of the investigation we did, because we concluded that, well, you could use Luxion C in such an array, you could use Luxion Rubix, but whatever you choose, it doesn't feel like the perfect solution. So we set out to find what is the best LED for this application, even if that LED doesn't exist yet. And to do that, we listed a number of wishes or requirements for this. On the left, you see a schematic of what such a potential LED array could look like. And this came from our concept analysis. So what you see here is an array on 3 colors, RGB, but this can also be more complex, like 6 or 7 channels, even housing 9 different color LEDs. It can be much more complex than on this picture. What do we need for this array to work well in systems? Well, we need maximum light output, and commonly you achieve that by just driving the LEDs harder. You want a small array size, which works best with small LEDs. Obviously, because we have a big thermal headache as well, we also want best performance out of the LEDs. We need to mix the colors well. We need to do some electrical routing to turn them on and off. And the thermal management needs to be optimized. So all the heat from the LEDs need to be dissipated away effectively. And a lot of these requirements are conflicting. An efficient LED is usually very big. An LED array that is small is difficult to manage thermally. An array with good color mixing often is very difficult to route. So all of these requirements we found are conflicting, which, well, we found as engineers obviously an interesting puzzle. But as we went along this concept study, we did get more and more respect for the engineers that are actually designing such systems. It's not easy to find the right balance, as I will show in the next few slides. So the next few slides, we'll dive a little bit deeper in each of these requirements to see what is the ideal LED for this requirement. First of all, we like to have a small package and it needs to be best performing. So let's have a look at this best performance. You can achieve that with a large die. As the LED chip becomes larger, you get higher flux out of the LED, and simultaneously the voltage you need to drive this LED gets lower. And both these effects combined result that you have high efficacy, high lumen per watt. On one hand, that's because of higher optical power coming out of the LED, and there's lower electrical power needed to power these LEDs. And those combined make that the thermal load of each individual LED is as low as you can get it. So a large die is preferred as it has its best performance, but also we'd like to have a small package. And obviously these two things are conflicting. So a good metric to target for is to maximize the chip area into the space you have available in the array. And there are some limiting factors there. For example, if you make a close-packed array of LEDs, you need to have some spacing between the LEDs just to be able to pick and place these LEDs on a board. And second, if we make an LED package, we need to keep some clearance of the LED chip to the edge of the package. And both of these metrics, even though they're small, they don't scale with what die size we use. So to keep the impact of these limiting factors as low as possible, we need to use large die because that will make us give the most packing of LED chip area in the array. So large die is preferred. Now let's have a look at color mixing. There are several ways of creating such an array. For example, you can put the LEDs side by side, making linear lines of the same color LEDs. And I depicted here 4 colors. This can obviously also be 6 or 7 colors, whatever you like. In the middle is a diagonal placement of LEDs, where already the pitch between the lines becomes smaller, and this aids in color mixing. And on the right, we have a quasi-randomized array, which is well mixed, so you no longer have clear defined lines or clusters of the same color. Now, for all of these arrays, your optic will need to do some level of color mixing. And that color mixing, that means either loss in efficiency of your optic or loss in performance of your lamp. For example, mixing better means a broader beam angle. But whatever you do, the mixed configuration will always be better than the linear configuration. Just because you need to do more work in the optics to do linear mixing compared to the mixed configuration. So whatever we choose, let's put the LEDs in a randomized fashion. So how to do that and also be able to turn them on. So here I depicted 2 different popular footprints of LEDs. Here on the left, there's the Luxeon ZES, which has a large thermal pad here and 2 electrodes for connecting the LED. This thermal pad is isolated, and if it's large, you would think, well, this is ideal for my thermals. But the routing is very difficult. If you try to do this on a single layer of copper, you end up in having mostly linear arrangements of these LEDs. So even though this is thermally ideal for color mixing, this is a very poor configuration. Then the alternative is to use an LED with a 3-stripe footprint. And this is our Luxeon C. It has a large thermal pad in the middle, and the anode and cathode are on either side of this thermal pad. This can very efficiently do diagonal placement of LEDs, and that already improves your thermal mixing a bit. Now, ideally, we like to go to a randomized configuration. And you could do that with a Luxeon C footprint, but it always makes a compromise. So here we had to space the LEDs slightly apart in order to put traces between the LEDs. So now we have a good color mixing solution, but unfortunately, we had to compromise on LED count. We cannot fit as many LEDs in this array. So to make a mixed array, a 3-stripe footprint is best. Now we have a closer look at this footprint as the footprint connects to the PCB. And there's several PCBs that have a good thermal performance, and I listed a few here. For example, you can put these LEDs on a ceramic substrate. Ceramics materials are already isolated, and that helps to dissipate the heat. The thermal conductivity is good, but ceramics are fragile. Then second is the insulated metal substrate. or MCPCB. So this separates the metal substrate from the copper tracks with a little bit of dielectric material. So the heat needs to be transferred through this dielectric into the substrate. And if you use a very good dielectric with good thermal properties, then the thermal properties of your system will improve. Alternatively, there's FR4 with filled vias. That means you drill holes in the FR4 and you fill those holes up with thermally conductive material. This way you can also make a good path to the heatsink. But our preferred solution is IMS with copper pedestals. So this is very similar to the IMS we talked about before, but it looks more like this. So the anode and cathode of the LED are on top of a copper of the PCB, which is separated from the substrate with a small bit of dielectric. So that's the same. But now in the middle, we have the copper of the substrate protruding and connecting directly to the thermal pad of the LED. And now if the thermal pad is big, this creates a very efficient path to guide thermal energy into the substrate. There's also a little bit of energy being conducted here in the anode and cathode and going through the dielectric down. But the energy that is being dissipated by the thermal pad, that's the majority path. So we need to enable an LED to be used with this copper IMS pedestals. And then you can drive these LEDs above 2 amp, no problem. So how does the heat get dissipated further into the system? So first of all, we encounter a thermal interface material that connects it to the heatsink. And in the heatsink, we have fans, and usually there's a fan blowing away the thermal energy. So a system works best if the thermal interfaces are optimized. So if this thermal interface is thin and well conducting, there are no air voids in the thermal interface. The same holds for your solder joints of the LED. And if you do everything correctly, then your thermals are optimal and you can reduce the fan speed or even eliminate fan. And that has big advantages if you think of a studio lighting scenario where you have a quiet scene. You don't want to be disturbed by the noise of the fan. So there, eliminating the fan or running it at a very low speed can have big benefits. Then back to the LED. So we also had to decide whether an LED with a dome or without a dome is ideal for this application. And that was a difficult one. So with a dome, you obviously have more light emitted from the LED. That's why we always like to use domes. But a dome typically needs to be 3 times the size of the chip. So it's best suited for big LEDs. But if you do that, then you can extract much more light, and that's up to 40%, especially in red LEDs. That's a really big benefit. And if you then have a thermally limited system, per watt of thermal energy, you can extract up to 60% more light from this LED. So that's great. You also have an advantage of being able to shape the radiation pattern to what you need. And I depicted here 2 different radiation patterns from an undomed and a domed LED. On the left, we have the radiation pattern of our Luxion CZ, which has an almost Lambertian radiation pattern. And I also depicted here an imaginary reflector that we might use in combination with this LED. And the green area here depicts where the reflector would accept light. So you would like to optimize your radiation pattern to have most light in this green area. And you can see already from the radiation pattern, there's a significant portion being emitted straight on and never interacting with the reflector. So a LED with a wide radiation pattern, like a Luxion C, would then be ideal because it aims more light to the reflector surface and therefore the system gets more efficient. So this speaks towards using a dome. But without the dome, we have a much smaller package size because we don't need to house that dome. So we can pack more LEDs together in our array. And Second, the optics that we might use can be very close to the LED. Think of a mixing rod can be almost touching the die. Another advantage of undomed LEDs is that they excite their neighbors less. What do I mean with that? Think of having a close-packed array and you want to have blue light. You don't want the blue light from an LED to enter the neighboring phosphor. And therefore the blue light gets converted into white as your saturation of your blue light goes down. So that's also an advantage of undomed LEDs. So here we could not conclude. So going back to our requirements, gave you already a flavor of the challenges we faced by deciding what is the best LED for this application. And we found that many of these requirements are conflicting. So we want to have a large LED to be more efficient. We want to have a small LED for color mixing. We want a large LED so the pads can be easier electrically routed, but we also want the thermal management to be ideal. We were struggling, but we did find a balance in these trade-offs. Let's go to the next slide and see what we think is the best LED for the close-packed multicolor arrays. So first of all, we want to use a large die. This creates the best packing, best die area packing in our array. And a difficulty here is that we have a family of colors, and all of these dies, they have a different chip architecture, different EPIs. So you need to find common ground here with the same die size. And the largest die we can use for this is a 2 square millimeter die. So that's nice and big. So that enables us maximum light output because we can drive this hard, and we have good performance because the large die makes it efficient. And because it's efficient, also the thermals look better. We can squeeze this large die into a package of 2 by 2 millimeters. So the 2 by 2 millimeters allows us to make small arrays with good color mixing. Then, you guessed it already, we do want to make use of a dome. We found it has many benefits. Of course, we have high light output, and we can make a wide radiation pattern to interact more effectively with optics. But what we also managed to do is to suppress the light that would normally go towards the horizon. So that has two benefits. We don't excite the neighboring LEDs with the blue light we actually want to have. And it has lower optical losses because usually the light that goes out of the LED horizontally, it doesn't interact with optics and is basically lost. So with the dome, we have maximum light output, we have the best performance with this radiation pattern. We have good color mixing, and obviously the thermals are also good. Another topic is the bottom of the LED, where our footprint is. And we already concluded before that a 3-stripe footprint would be ideal for this application, as it allows more complex routing. But we don't want to compromise on packing density. So we want to put these LEDs as close as possible together and still be able to make complex multicolor arrays. Here I depicted 4 colors, but can easily also be 6. And what we did here is we enable a complex array by intentionally choosing the copper footprint of the LED to be smaller than the LED package. And that allows us to put traces between the LEDs. So now you can route this green LED to that one and continue without compromising on your packing density. So we can make very complex arrays, good for color mixing. We have solved the problem of electrical routing, and we have still a big thermal pad, so the thermals also look good. We were happy with this. Actually, we were so happy that we decided to make this a product, because this is such a a big advantage compared to what we already have in our portfolio, that we will launch the Luxion CES color line. This will be a multicolor family of multiple colors. We will have blue, green, cyan as direct colors. That gives you very deep saturation. We'll have 2 phosphor converted colors that will use our lumileds platelets. And with that, you have maximum saturation and maximum efficiency out of the LED. We'll have 2 reds, conventional red and a deep red, and we'll complement this portfolio with whites. We have engaged with customers already that are interested in using this, and so far it seems that the balance we have chosen on all of our requirements, they pay off tremendously. So we got really good system performance of about 40% improvement on the system level, and this is tested by our customers. So we are very happy to see that this balance turns out to be so effective. We have many lead customers that want to implement this immediately. So what do you use it for? This will show up mostly in studio lighting and also in entertainment. So I hope you're just as excited as me with this product line. I look forward, and hopefully you as well, in the short future to see our next Netflix series to be illuminated by this LED. Or the future concerts we'll be going to, that you'll see the very high power and strong color saturation of these LEDs in the shows where they will be putting up in concerts. So if you're interested in this product, want to have more information, please send us a message. We have opened up an email address for this particular color line. That is color@lumileds.com. I'm looking forward to hearing from you on your questions and interest on this product. Thank you very much.